Okay, so what I'm going to do is try and project my voice for the next 30 minutes. Can people at the back hear me? Yeah, they're nodding. Good, right. So I'll stand here in the position of the priest and I'll give you my sermon. Okay. So what I'm going to do this morning is tell you about the heliostat, what it is, but also its importance from the point of view of Einstein's theory of general relativity. So that's the theory which actually predicts gravitational waves that Mike Cruz will talk about in a few minutes, and also a lot of very interesting effects such as black holes. So the story goes back to some degree to the sort of 1840s, 1850s in Ireland, when it was a sort of golden era of astronomy in this country. A lot of people would know that at that time, around 1850s, 1860s, we had the largest reflecting telescope in the world. The telescope here on the left, which is in Burcastle in County Offaly. But over here on the right is Markree Castle, which had the largest refractor in the world. So the largest telescope with a lens in the front of it as opposed to a mirror. So we had at the same time the largest reflector and refractor in the world. And out of that work in astronomy grew an industry. It started with a man called Thomas Grubb. He built a lot of instruments for around the world, and then his son, Howard Grubb, took over the business. Here's a picture of Howard. His firm was actually based in Rathmines in Dublin. If any of you are ever in that part of the world, near the clock tower in Rathmines, which is not that far from here, you'll actually see a place called Observatory Lane. And up Observatory Lane, Howard Grubb manufactured telescopes for all around the world, but he was also the inventor of the submarine periscope as well. So Holland, many of you will know John Holland developed the modern-day submarine, an Irishman as well, and Grubb developed the periscope for the submarine. He was a bit of an inventor because he also invented the first anti-dazzle light system for cars, and he also invented the idea of the radio-controlled clock, which a lot of people will have in your home today. So Grubb, at the height of his business, had 400 employees based in Rathmines, working in what we can only call the smart economy of the time. We had a smart economy going back many, many years. It's not a modern day invention of the politicians. Here's actually the building in Rathmines where they constructed the telescopes and tested the telescopes from the top of the building. What I love about this picture is the clear consideration of health and safety, as you can see. And here's one of Howard Grubb's telescopes. It's the Great Melbourne Reflecting Telescope. This is actually in Melbourne. I think this guy on top of the roof there is definitely posing. But the telescope itself was used up until approximately 15 years ago for the hunt for dark matter. So Grubb's telescopes were used up until almost the present day. Here's another one, which is the largest refractor on mainland Europe. And that instrument is in the Royal Observatory in Vienna, has been recently, the dome, etc., has been refurbished. And that was also a Grubb instrument. So he was a very, very important manufacturer of telescopes. Now the story kind of starts back in 1900. Howard Grubb was a member of the Royal Irish Academy. The Royal Irish Academy got together with the Royal Dublin Society to plan a trip to Spain to observe an eclipse. So there was an eclipse around May, quite close to Madrid is where they decided to base their camp. And I rather like this picture. Let me get the laser. So this is Howard Grubb sitting here. This is a guy called Jasper Joly, who was director of Dunsink Observatory at the time, which was part of Trinity College. And what I like particularly about this picture is that this guy here his name is Wilson. He actually did a lot of work to do with solar observing. He was based in Daramona not too far away from Dublin. He had his own observatory there. And he clearly sees Spain in 1900, you know, with the pit helmet as sort of deepest, darkest Spain. Right? In comparison, Howard Grubb's son, Rupert here, clearly sees it according to the more modern idea with the straw hat and, right? So obviously things were changing. The attitude to Spain was changing at the time. So they set up the experiment in Spain to observe the eclipse. Here you see Jasper Joly. This is a photographic plate here. This is a 20-foot tube, and at the end of the 20-foot tube, right, is, you can't see it very well here, I'll show you some better pictures, is this instrument here. It's a Lestat. All it does is take the light from the sun. It's a mirror, as you'll see when you look at it more closely, and the mirror moves so that the light from the sun is fed into the telescope. What it means is you don't move the telescope, okay? It's actually just uses a mirror to point down the long tube, okay? And that way you can have a really long telescope like that, long focal length, without actually moving the telescope around, okay? So that's the basic principle. And they recorded then the eclipse in 1900, in May 1900. And here's an actual picture from that expedition in 1900. And you can see some flares coming off the sun as well. And this was taken with the Lestat, but also the Royal Irish Academy that had a 4-inch lens, which was specially made by Howard Grubb and Rathmines, as was this instrument here. We have the lens as well, by the way, and the significance of that I'll tell you in a moment. But you can see the prominences coming out from the sun. And it's amazing to think this is a picture taken in 1900. Okay. One thing I did was actually compile the pictures from the time. Oh, unfortunately, it doesn't, for some reason, it doesn't come out very well. The usual story, it comes out really nicely on the laptop. But anyway, to cut a long story short, I've put a number of these pictures together, and you can actually see what's called a coronal mass ejection, an event in which the sun is actually throwing out material at very high speed of order several hundred kilometers per second. And you can see this, and it's the first recorded coronal mass ejection. Okay? There was one known about a number of years beforehand, but that wasn't actually photographed. Now, we'll fast forward to 1915, towards the end of 1915, December 1915, so just 100 years has passed, and Einstein published his general theory of relativity, and one of the major predictions of that theory was that light would be deflected by a gravitating body, such as the sun. So what you have here is, imagine you have a star up here, and the light of it comes along the blue line here, and then, as a result of the sun, the light is deflected. Fine. Okay? But from Earth, when we look out, you would see the star actually had appeared to move, right? So the light is actually bent around, and it makes the stars move away from the sun. That's fine, but we have to observe stars near the sun, which is a bit difficult. It's a bit bright. So of course, what you do is observe during an eclipse. So when an eclipse occurs, when the moon goes in front of the sun, then in that situation, the stars appear momentarily, maybe for a minute or so. You can photograph them, measure their position, and if the stars start to move away from the sun, then, and by the amount they move away, you can test the general theory of relativity. And what Einstein predicted was a very small shift, 1.75 arc seconds. Give you an idea how small that is. It's equivalent to, you know, the distance between a pair of headlights at, I think, about something like about 40 miles, 30 miles, something of that order. Okay? So that's the tiny little angle that you've got to measure. Now, there was a problem. 1915, the First World War was on. So there was no way anybody was going to an eclipse site. But what happened was the Royal Society in Britain got together with the Royal Astronomical Society, and they put together a committee, wonderfully called the Joint Permanent Eclipse Committee. I don't know why. No eclipse is permanent, and hopefully no committee is permanent either, right? But anyway, that the committee doesn't exist anymore. So there you go. Anyway, the Joint Permanent Eclipse Committee decided they were going to mount an expedition to test Einstein's theory of relativity as soon as the war was over. Okay? But they had a problem, and the problem was this: their equipment, which had gone to Russia in 1914 to see an eclipse, had been confiscated. So the war broke out around the time of the eclipse in 1914. The astronomers got out, but the equipment was taken by the Russians. And of course, after the war had finished, you then had the Bolshevik Revolution, and so they didn't get the equipment back even then. It was only in the 1920s, the middle of the 1920s, that they actually got the equipment back. Right? So they didn't have enough equipment. Fortunately, a Father Corty, who was in a place called Stonyhurst, a school near Liverpool, that sort of area, realized the Royal Irish Academy, he had connections with Ireland, had equipment that could be used. The same equipment that had been used in the 1900 eclipse. Okay? So, two sites were chosen. Prinkep, which is an island off the coast of West Africa, and Sobral, which is in Brazil and is somewhat inland as well. So these were the two sites that were chosen based on the fact they were on the path of the eclipse in May 1919. And what they did was they sent out two expeditions. And it was thought this was an extremely favorable eclipse. And the reason was very straightforward. The sun happened to be, during that time, in a group of stars called the Hyades. So if anybody knows the stars, you'll know of Taurus, the bull, and then the Hyades then, this is the horns of the bull, and the Hyades extend all the way up here. And the sun was actually in the Hyades. What that meant was when the eclipse occurred, there were a number of bright stars which they could make the measurements of, and so test Einstein's theory. So it was a perfect eclipse for what they wanted to do. The eclipse instruments were in Prinkep, actually Grubbs instruments dominated, 13-inch Grubb lens fed by a 16-inch mirror Lestat from Oxford, and in Sobral there was a 13-inch Grubb lens fed by a 16-inch Lestat from Greenwich Observatory, the Royal Greenwich Observatory, and then a photographic lens, a 4-inch photographic lens, and the Lestat that you see here were essentially backup equipment. right? As I said, they were short of equipment. They wanted extra equipment just in case something would happen. And of course, something did. The expedition to Sobral, by the way, in Brazil, was led by this man, Andrew Crommelin. Andrew was from County Antrim and went to school in County Antrim, then trained in England and actually led the expedition to Sobral. But the overall, and Princeps was led by Arthur Stanley Eddington, who was a famous theoretical astronomer, theoretical physicist from Cambridge. So he went to Princeps off Africa, and Crommelin went to Sobral. And here's the equipment in Sobral. There is the actual Celestat. It's just here. And as I said, it's feeding the 4-inch lens and the tube. So just like in 1900. Same arrangement. And here's the bigger Celestat feeding a bigger telescope here. Okay? There's a bit of a wedge here. And the reason for the wedge, by the way, is the fact that it was in the southern hemisphere. And so they had to allow for the tilt, the effect that it was in the southern hemisphere, and so the sun was at a totally different angle. Anyway, to cut a long story short, Princeps, they recorded a few stars. The weather was not so good. The sun kind of darted in and out from clouds. Sobral was perfect, right? Except there was one problem. The main instrumentation had overheated. It went out of focus, and so everything relied on this equipment here. So the 4-inch lens and the Celestat produced the best results. And in papers, the papers which were written at the time, that's clearly stated. Now, I apologize for this picture, but this is the 1919 eclipse picture. The actual proper photographic plates went missing, right, from the Royal Greenwich Observatory. Nobody knows where they are. Okay? Now, we may have located copies in the Maritime Museum, and that's something which we're in the process of checking now. It would be nice to have them for 2019, of course. Okay? And, but very faintly, and you can look at it closely on the computer, there's 2 faint stars. There's a star called Kappa Tau in the Hyades, a double star. And they were able to make measurements of that double star, plus a few of the field, and they found Einstein was right. So the results were published to great fanfare. Just to emphasize, this is the famous paper that proved Einstein was right. And here you see, in summarizing the results of the 2 expeditions, the greatest weight must be attached to those obtained with the 4-inch lens at Sobral, and of course the Celestat that fed it. Okay? And as I say, we have rediscovered the lens as well. This piece from the Times, I rather like, of the day. The subject was a lively topic of conversation in the House of Commons yesterday, and Sir Joseph Lamore for Cambridge University, on arriving at the lecture before the Royal Astronomical Society last evening, said he had been besieged by inquiries as to whether Newton had been cast down and Cambridge done in as a result of this German scientist's theory being proven correct. And here we see Eddington with Einstein, and of course Eddington was very famous as a result. Again, and I don't have the time to give you all the details, but very briefly, I discovered through a number of papers and letters that the equipment had actually been sent back to Ireland in 1947. Okay, through archives in the Royal Astronomical Society, who were very, very helpful with this, and the Royal Society, the equipment had been sent back. And then I found the actual equipment, and this is the Celestat. It was in this sort of state, but the French, in particular the Madonna Observatory in Paris and the CNRS restored it. It went into an expedition in Paris late last year, and so now it's back in Dublin. And this is the 4-inch lens that was used for the tests as well. And that was discovered in a box, in the basement, the usual sort of romantic notion of where you find this sort of stuff. Okay, but there's an amazing twist in this whole story, which kind of astounded me when I discovered it. And let me give you an example. Every year I'm brought up to, I did some work on Newgrange back in the late 1980s to prove it actually was lined perfectly for the sun in 3200 BC. And I think many of you would know about Newgrange and the alignment there. So every year I'm kind of dragged up to Newgrange on the 21st of December, which is supposedly the shortest day of the year. But once in 4 years, it's actually the 22nd of December. And that's because of the leap year effect. The leap year means that the shortest day gradually goes from the 21st to the 22nd, and then, because with the leap year, then we put in an extra day, it goes back to the 21st, right? I rather like it because all the great and the good and the politicians are up there on the 21st, and I'm told to keep my mouth shut, that it's actually the following day. But anyway, leaving that aside, the point is there were 2 eclipses which both occurred in May. Right? One was on the 29th of May in Madrid in 1900. The other was the 28th of May. Okay, so close, I thought initially. But then I realized one was in the morning, one was in the afternoon, and one was a leap year, and the other one wasn't. It turns out the sun was in exactly the same place in the sky for both eclipses. Just purely a freak coincidence. Okay, well, you can see here, this is a simulation from software of where the sun was, and there's Kappa Tau, and this is the eclipse near Madrid, May the 28th, sorry, May the 28th, not the 29th, 1900. Okay, here is the Sobral eclipse for 1990, there's Kappa Tau, and there's the sun. Okay, it's upside down. Remember, this is Brazil, this is Northern Hemisphere, that's why, okay? But it's exactly the same place. So, what we have is 2 eclipses which were done in exactly the same place in the Hyades, 1900 and 1919, with the same equipment. Just a freak coincidence. It was like 1 in 3 or 4,000 or something like that, chances of it occurring, but it did. But the interesting thing also was that back in 1900, the astronomers then also photographed the eclipse, as you see, right? So the same stars should be in the same photographs. And in fact, the reason why they were photographing and even looking at the stars was, okay, they wanted to look at the sun and the corona and all the rest, but the main reason was they were looking, I couldn't resist this, Vulcan. So at one point it was theorized there was a planet inside the orbit of Mercury. This planet was nearer the sun, in other words, than Mercury, and they were looking for this planet. And why did they think it was there? They thought it was there because of Mercury was moving faster than it should have. Okay? And that effect turned out to be a general relativistic effect. So they were looking for a planet, and in the end, Vulcan turned out to be a myth, and the whole effect was due to general relativity. So, back 1900, I started looking at the photographs from 1900, This is one's from Shabo Observatory. It's near Oakland in San Francisco. There's Kappa Tau. Same stars. Right? And there are stars also in the field around this as well. And it had actually been suggested by this man, Freundlich, to Dyson, who was the overall responsibility for the eclipse, the royal astronomer in the UK. It actually suggested to him to look at these old plates. Okay. How my time was? 5 minutes? Okay, we're nearly done. 2 or 3 minutes, okay. So, anyway, Dyson in 1917 actually came up with some measurements from some old plates. He found that there was an eclipse coming up in 1919, and he was the person who actually proposed the expeditions with Eddington and then also with Crommelin. So he realized the technique would work. He used an old eclipse plate and showed it would work, but said, he didn't have enough data. But then I discovered who had actually been observing the eclipse, the same eclipse in 1900, only Dyson. So we had photographic plates of the eclipse from 1900. And it turned out when I went to the archives, there was only 3 sets of plates, and he published the results from the wrong ones. There is Dyson's plates from Portugal, 1900. There's Kappa Tau. Why didn't he publish this result? We'll never really know, but the problem was probably this. Eddington was a conscientious objector. He did not want to go off to the First World War. He said he would go to prison first. Around this time, Dyson came up with the idea of Arthur Eddington being sent off for the expedition. Eddington appeared before a military tribunal. I have the transcript in which it was said, with a letter from Dyson, there would not be another eclipse like this for 500 years. That's correct. But you have to believe they didn't look back 19. Okay? So Eddington ended up being excused by virtue of the fact that he was testing the general theory of relativity. He was a theoretician. He went, in fact, first-year labs, I'm sure you'll appreciate this, in Cambridge, and he was such a disaster in first-year labs that it was suggested he be moved into applied mathematics and out of the lab. So he was the one that was sent to lead the expedition. So what I suspect is that Dyson, at least Dyson, realized there would have been a problem if he'd have published these results. He may not have got the result out of this that he wanted to prove with sufficient accuracy, but nevertheless, I think he would have muddied the waters if he had actually published the plates which he had in his hands of the same eclipse. So this is the Lestat. As I said, it was discovered only about 1.5 years ago, and it's rather nice that coming up to the 100th celebration of the Eddington Dyson expedition that we have now the Lestat and actually the lens that proved Einstein right. So thank you very much. Thank you.